Okay, so I just want to run through a couple of examples, some harder ones in this moment's work, and then later on next week I'll leave you some exam questions to have a go at. We're only sort of halfway through this topic. There's another chunk of the topic to come later on in at the end of the course, in fact, when we've done more work on friction. But for now, I say we'll just look at some harder examples that you can do right now, and then obviously we'll return to it later on. So the first example, okay, has a beam AB, which is being suspended by two wires coming off like so. The wire on the left is coming off at 30 degrees, the wire on the right is coming off at 50 degrees. Okay, the beam itself is non-uniform with a mass of 5g, and we'll call that distance x from A. That's what we're going to find in part B. First thing to consider is, well, we've got these two tensions in the wires, they're pulling out angles. Because the angles are different, it means that the tensions have to be different. So we'll call them tension A and tension B. Okay? So the first part of the question asks us to find the tension in the wires. So remember, our general repertoire is resolving forces upwards, resolving forces across, and taking moments. That's our general repertoire. They're the options we have for solving these kind of problems. If we take moments, we're going to end up with too many unknowns essentially. So the first bit we're going to do is resolve forces. So I'm going to resolve forces up. So if I do forces up, we've got this tension A force here. If you think of how this force splits, so it's force out and up, so that's TA cos 30 and TA sine 30, okay, the component of it. So TA sine 30 plus tension B times sine 50, it's got to be equal to force down, so 5G. Two unknowns, so we can't solve it yet. Well, let's resolve horizontally. Well, in this case, therefore, TB and cos 50 has got to be equal to TA cos 30. And if we rearrange this equation, say for TB is equal to TA cos 30 over cos 50. Okay, which looks something, so we're going to end up with something like that. If we then plug this into, so we're going to take this TB, put it in here. So TA sine 30 plus TA cos 30 over cos 50 times sine 50 has got to be equal to 5G. Well, we can go through and solve this. Okay, so if we solve this, so TA brackets sine 30 plus cos 30 sine 50 over cos 50 is equal to 5G. Divide it through by the bracket, and we'll find that the tension at A out here is 31.98 newtons. Feed that back into that equation, and we'll find that TB is 43.1 newtons. So we've got TA, that's 31.98, or 32.0, and 43.1. So we're resolving forces. Vertical force, TA sine 30, and obviously up here, we'll put this one on. So that's TB cos 50, and upwards force of TB sine 50. Okay, and that leaves us with the stuff there. If I then move on to part B, so part B then asks us to find where the centre of mass is. Well, I'm going to do this by taking moments about A, it's in equilibrium, so we know it's going to be equal to 0. So 5G times x, force, times distance, is equal to my force, So this TB cos 50 force acts through point A, if you think of the force line. So that has no moment, that one has a moment. So TB sine 50 times by the distance it is away. The whole beam itself was 4 meters long. Rearrange that, or put your TB in, which we know is 43.1. Solve for x, and you get 2.70 meters. Okay, so angled forces, okay, just split them into the components, vertical and horizontal components, and then you can resolve, and also you can take moments. Question 2 starts to look at the idea of a hinge. So we have a vertical wall which looks like this, and we've got a horizontal non-uniform beam coming out of the wall like that. So there's my beam AB. We're told we've got a wire coming up there which is holding it in place at an angle of 35 degrees, and it's non-uniform with a mass of 15 kilograms, okay, which is 1 meter from there, which leaves us as 2 meters because the whole thing's through. What I want to consider though is, what do we mean by a hinge? So there is our hinge. Well, obviously that means in theory the thing can pivot around point A, can move up and down. What we need to consider is the forces at that hinge. There is forces at that hinge. Okay, that's smooth hinge. The way we consider these forces is to say there's a horizontal force, which I'm going to put as going inwards, and a vertical force, which I'm going to put for now as going upwards. It doesn't really matter which way you put them, because essentially we're going to be looking at positive and negatives. So if an answer comes out as negative, just means the force is going in the other direction. If you think of it logically though, horizontally the forces have to balance. So if we've got this T force pulling in left, this horizontal force has got to be pushing out right to balance off that force. So if you think of this force here, so that's T sine 35 going up, and T cos 35 going in that way. So the first question is, how do I find this tension here in the wire? Well, if I look at this diagram, I can take moments about any point on the beam. Obviously the logical place is to take moments at A, because those two things won't appear. So if I start by taking moments about A, those two forces won't appear anymore. So take moments about A, 15g times its distance 1 there. It's got to be equal to the force, so again, that has no moment. Okay, only this bit here. This is the only one which causes a moment. That one has no moment. So it is equal to T sine 35 times the distance, which is 3 meters. If you solve that, you'll find the tensional force is 85.4 newtons. Okay, so that's part A done. That's find tensional force. Part B asks to find the resultant force at the hinge. That basically means I need to find this horizontal force and this vertical force. To do that, I'm going to start resolving forces. There's no point taking moments again, realistically. Okay, the best way is generally to resolve, it's quicker. So if I resolve horizontally, my horizontal force at A has got to be equal to the horizontal force at B. Obviously we know what the tension is now, so therefore, yeah, my horizontal force at A being 70 newtons. If I resolve vertically, well, VA, the vertical component at A, plus T sine 35, it's got to be equal to my forces going down, so 15g. Again, using the tension from there, I can find that the vertical force at A is going to be 98 newtons. So now if I consider at A, we have a horizontal force going this way with 70 newtons. We have a vertical force going this way with 98 newtons. this is my resultant force. And obviously we're going to get that by using Pythagoras. So my resultant is equal to root 98 squared plus 70 squared, which will give me 120 newtons. And if you ask for direction, well, it's acting up and right, so up and away from the wall. Question 3 is the idea of looking at ladders and walls. This comes up quite a lot. So question 3, we have a ladder resting on a horizontal floor and against a vertical wall. Okay, so here's my ladder going in there. That's point A, that's point B. Okay, we need to put some forces on. We're told that this is a smooth wall. Okay, so it's a smooth wall, so no friction. What that means is there's no vertical force, so that means there's only a reaction force at B. There's nothing to kind of stop it sliding down because it's smooth. Okay, so there's only, so smooth wall, so no friction, only reaction. Okay, you're told it's a rough floor. Well, that means we've got a reaction at A, but we're also going to have a friction at A in there as well. If you think logically for the ladder is going to want to fall down that way, so the friction is going to hold it in place. We're told it's a uniform beam, so we've got 30G for the mass of it at a distance of 1.5 metres, and we know that there is a person of weight 50 kilograms who is 1 metre from there, so therefore is 0.5 metres from there. So there's my midpoint. I'm going to call that point C. So there's our diagram. Okay, so forces involved. These diagrams are so vital. Rough floor, so we have friction and we have a reaction. Smooth wall, so only a reaction. Mass of the ladder, mass of the person. Okay. What it wants us to find is these three unknowns, so that's what we're trying to find, so 1, 2 and 3. Well, like I said, we have three options: resolve up, resolve out, or take moments. Well, let's start with resolving upwards then. Well, what forces do I add up? Reaction at A, that and that. Those two things have no vertical, so therefore the reaction at A has solely got to be 80G. 30G plus 50G. Okay. Next bit, well, if we resolve horizontally, what forces are going horizontally? Which are the reaction at B and friction at A. So the reaction at B has got to be equal to the friction at A. Okay, that's useful to know, but doesn't give us any numbers. So therefore my last option is to take moments. Most logical place is down here, A, because it removes those two from the equation. So I'm going to take moments from A. These two forces are going to cause clockwise motion. That reaction at B is going to try and cause an anti-clockwise motion. So let's start with the forces. So we've got 30G. So that 30G is a distance of 1.5 metres, but they're not perpendicular. If you think of your force line, so the work we did a couple of lessons ago, this is my perpendicular distance here. So this bit here is my perpendicular distance for the 30G. We know that that angle in there is 60 degrees, so that distance has got to be 1.5 cos 60. Okay, so that is my perpendicular distance for that 30G force. Plus 50G times, so that distance there is 2 metres. Perpendicular distance is this bit down here. So if I remove that one, so for my 50G force, if it comes all the way down to that point there, this distance down here, there is my perpendicular distance. So that's 2 meters, again, times cos 60, minus, so the RB is going the other direction. Okay, and again, so think of your force line. So there's my RB force line. Here's my point. So this distance is my perpendicular distance for that RB force line. Okay, from that point A. So how far is this distance? Well, that distance is 3 meters, and then 60, so it's going to be 3 meters times by sine 60, and that's all going to be 0. So that distance there is my perpendicular distance for that RB force line. If you solve that, you'll find that the reaction at B ends up being 273 newtons, which obviously is also equal to the friction at A. So 273 newtons is my friction at A and my reaction at B. Last question, okay, is a rod on a peg. So we have ground, which looks something like this, and we have a rod which is coming off that ground like so to a peg. Well, we know that is 3 meters high. We know the rod is uniform, so it's got a mass of, or weight of 4 newtons. That is going to be 3 meters from there. That's going to be 1.5 meters, and that's going to be another 1.5 meters, because we know the whole length of it. So from A to B is all 6 meters, so A to the centre of mass is going to be there. This is the point C. Okay, so other forces, we know it's a rough floor, so we've got a frictional force at A and a reactional force at A. Okay, rough floor, friction force, reaction force. This is a smooth peg, so it therefore only has a reactional force. Okay, smooth peg, so therefore no frictional force. The other thing we need to consider, just before we do any more working, is we've got this angle theta here. Well, if we look at the triangle from A to C, this triangle here, we know that that's 3 meters and that's 4.5 meters. If you use Pythagoras, you'll find that that is 3 root 5 upon 2. That angle in there. So therefore, if you work out the cos theta ends up being root 5 upon 3. Sine theta comes out as 2/3. Okay? Remembering, cos theta is adjacent over hypotenuse. Sine theta is opposite over adjacent. Sorry, sine theta is opposite over hypotenuse. So, part A asks us to find this reaction at C. Well, if we look at the diagram here, we've got some unknowns here, unknowns there. Obviously, the bit we want, the easiest way is if you take moments around A, these two forces will disappear because they have no moment. So moment around A going that way. For the moment around A, we've got this 4 Newton force, okay, times by the distance it is, and again we need a component because they're not perpendicular. So that is my perpendicular distance. So it's 3 meters times by cos theta, which is there. That's going to be equal to RC. Because RC is perpendicular, it is solely 4.5 meters. So times 4.5, which if you solve, gives you an RC, reaction C of 8 root 5 upon 9. Okay, fine to leave it in an exact form. We're dealing in newtons, no G involved or anything like that. We're taking moments around A, 4 times 3 cos theta, perpendicular distance, is equal to RC times 4.5. Next bit is we need to find friction A and reaction A. Again, we've done our moment, so therefore we're left. So if you think resolve horizontally, resolve vertically, take moments, well, we've done that. So these are the logical choices. The only bit that I want to add onto the diagram is onto the RC here. Well, if I put a triangle in there, if you do a little bit of angles work, you'll find that that angle theta is the same as that angle theta. So therefore we've got RC sine theta pointing left, RC cos theta pointing up. Okay, so again, this resolving forces work, it comes up again and again and again. So therefore, if I start now, let's resolve horizontally. Well, horizontal forces is this friction at A and this RC sine theta. So in other words, friction at A is equal to RC sine theta. So the friction at A is 8 root 5 upon 9 times by sine theta, so 2/3, which ends up giving my friction at A, where are we? Is 16 root 5 over 27. If I resolve vertically, vertical forces, RA plus RC cos theta is equal to 4 newtons. So RA is 4 minus RC, 8 root 5 upon 9 times by cos theta, root 5 upon 3, which if you work it out gives you 68 upon 27. So I can't express enough the importance of a nice big clear diagram. Don't butcher a diagram you're given, draw your own and draw your forces on it. Okay? Think of the components. Okay, so if RC is here, RC cos theta pointing up, RC sine theta pointing left. Think of the perpendicular distances, so that 4 Newton is 3 cos theta away from that point A. Okay, and have a go at the questions that I've given you.